Hey everybody, this is Larry. This is February 14th. Happy Valentine's Day. Happy New Year for those of you celebrating during the New Year. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about today's farm and also the contest in general. I did okay. I'm doing a brief update. I finished about 129 for something like that. But most of the issue was that I just was a little bit sloppy with respect to edge cases. I missed 2 edge cases for a 10-minute penalty where everyone finished, not everyone, but like all the top people finished like in 15 minutes and I had 10 minutes of penalty alone. So that knocked me down a lot. So my advice for you, slow down and make sure you do all the edge cases because I rushed it a little bit. Anyway, today's problem is graph bipartite. So I usually solve these live. Going for my thought process, so if it's a little bit slow, just fast forward or watch it on 2x or something. Anyway, okay, so given an undirected graph, return truth is bipartite, right? Okay. I mean, this is a little bit, how do you say this? So basically, this is a standard algorithm. And I say standard not in a way such that, like, I'm not saying that you should already know it. I'm just saying that if you don't know it, it's fine because it's in the textbook somewhere and you should just learn it, right? I mean, it's hard to come up with these things if you haven't done it before. That's what I mean by standard. And I would also say that it, as long as you kind of learn enough how to back out of it, then this should be okay as long as you have the tools to do it. Because for me, like I actually don't remember all the details of how to find whether a graph is bipartite, but I do remember a few things that I'll share with you here. I also did the contest in Java. That's why it's asking me in Java. But and again, this is actually similar to the last problem. This is where there's I'll be surprised if there aren't good YouTube videos and resources about this. Like I said, it's a standard graph problem that like I very much expect. There's a standard answer or like standard video to explain this. But that being said, I'm going to try to do a very brief explanation. Let me pull up my printing thingy. Okay. So let's say we have some nodes. Let's make the colors a little bit more colorful. So let's say we have some nodes and then some edges, right? So the idea behind a bipartite is such that, I guess this isn't bipartite, but such that, all the nodes are on one side or not half, but all the nodes are on the left side and the other nodes are on the right side. And you could kind of put a divide in it such that, if you draw a line vertically, all the nodes on the left side, there's no edges between any of the nodes on the left side, and there's no edges on any of the nodes on the right side, right? So that's basically the idea, and you could probably read the problem. I think it mentions this anyway. So idea here is, for learning, is that you start by coloring a color. So in this case, let's just say black, and then everything that's next to black, which is, you look at these 2 edges, everything that's next to black has to be the opposite color. In this case, white, but usually it's black and white, but we always start with black and white, so it's a little confusing. So let's make it black and yellow, okay? So now all the colors that are next to black are yellow. And then now we do the same thing where we look at all the yellow nodes. Let's look at this node for a second. And then we look at all these nodes and then look at similar all the neighbors of this node will have to be a different color. So this is black in this case. And then now that you visit every node and it's good, then you know that this is bipartite. Let's just say, for instance, let's say, we're processing, oops, where's the red color? Let's say we're processing the node that's still in the yellow box. And then now we go, okay, all the nodes next to this yellow node has to be black. So this is black, this is good. But then now as we try to turn this yellow to black, you can kind of see that, well, it cannot be 2 colors, right? So now that we see the 2 colors, then we know that it is not possible. So that's basically the idea. It's kind of like greedy in a way. And you can actually implement this with both depth first search and breadth first search. But that's the basic idea. Again, this is a standard-ish problem, or like, yeah, standard-ish problem. So I'm not going to go that much into the mathematical proof. There are probably good videos for this, and if you know one, put in the link or put in the comments below. I'm a fan of sharing or whatever. But that's basically the idea, and I'm going to, with all that known, we're going to solve this. And also, just taking a look at the constraint, which is, wait, what's the input? Okay, so these are you're given an edge list, right? It's a list. Oh no, this is an adjacency list. So 0 is connected to 1 and 3. Okay, so you're given an adjacency list. So this is v, and this is y per object. So in this case, v is equal to 100. Y is potentially less, 100 square, or 100 choose 2 maybe. But yeah, but that's basically the constraint. And because we can do this in a depth first search or breadth first search in O of v plus y time, this should be good enough. Yeah, and this is again a standard algorithm. So I'm going to, usually I actually do this in, usually I do this in depth first search. So today I'm going to practice breadth first search. And let's get started then. Yeah. Okay. So basically, let's start with let's colors is equal to, oops. Let's start with n is equal to the length of graph, and I'm going to try to explain as much as I can while I'm coding. But yeah, colors is equal to, let's just say 0 O times n, and here we can maybe use a color map. So the general notation is back, I think it's black, white, and gray, but maybe I'm wrong. But as long as you have 3 colors, it's fine. So let's just do any 3 just for fun, and because it's President's Day tomorrow, or maybe the day after, I don't know. I'm going to use red, white, and blue because I'm American. So let's just do red is equal to, okay, so white is equal to 0, equals unvisited. Red is equal to 1, blue is equal to 2, right? So we can just set this up, is equal to 0, red is equal to 1, blue is equal to 2. So then now we just set them all to right. Oops. Okay, I cannot type. But yeah, and then now we do a for loop. We go for x is in range of n. Let me double check to look at the constraint, because I just wanted to see whether this is 0 indexed or 1 indexed. That's basically it, because sometimes this varies a lot depending on who they ask. So okay, so now let's say we have this, and then if colors of x is equal to right, that means that is not visited. So we should, if it's not visited, then we can just color it any color, right? So we can just, I don't know, go color x, say, and we can put it in a helper so that it's easier. Start, I guess. Oh, I guess we already given the adjacency list, so we don't have to worry about any. Sometimes you might want to pre-process the list or something like that, but in this case, I don't think you need it, but I could be wrong. We'll see. Let me take a look at the input real quick. Yeah, I feel like that's right. Okay. So yeah. So we're going to do breadth first search here in this time, but again, in theory, you can do whatever you like. Q is to go to collections.deck. So I'm using deck again because deck is a superset of Q, and it's common way of doing things in Python. So now we set colors of start is equal to red, and then we again, sometimes I put in a Q function. It's up to you. It doesn't really matter per se, or like it, maybe it's more readable. Maybe I should do that more as a habit. That's but at least for now, it's okay. Okay, so let's just say, red and start, because we don't really, there's no distance. That's what I was thinking of, whether there's any sort of distance metrics. But yeah, so then while this, you get the the color and X. Maybe U. Maybe it's fine. Q.pop left. Okay. And then now we look at all the adjacent edges. So for we in graph of X, okay, we can write. So that's just. I need better variable names. Okay, let's try that. Kern color. Also in Python, to be honest, you generally want the underscore notation. The kebab, is that the kebab case? But just to keep it consistent with the way that they do it, I do it with camel case. But next color is equal to how does that go? Red if current color is equal to blue, else blue, right? This is a ternary statement. Put in a bracket just in case. So yeah. So if color sub v is equal to white, then we want to what you might call it. Then we want to color it, right? So we set color sub v is equal to next color, and then we put it on the queue. Next color v, right? Else, that means that this is already colored, so we have to check if color sub v is not equal to next color, then that means this is no good, so we return false. Otherwise, we return true at the very end after we unqueue everything. Yeah, and usually for breadth search you need a visited array, but in this case we kind of implicitly use the colors array to show that it's unvisited, right? Because we only want to visit colors that are white anyway, white. And then from here we can actually add a check here. If this is not colorable, then we return false. Otherwise we return true. I think this is roughly it. Could be wrong. Let's see. But that's why we test them. Okay, well, we get the first answer right, so that's at least a little bit helpful. I would also say for these problems, where the result is binary, I mean, by binary, I mean like it's true, false, you actually do want to test more test cases, because you may just get lucky and get the right answer, or unlucky maybe. So you definitely want to check. I'm a little bit lazy though, and you know, for the purpose of keeping the stream fast, I'm gonna give a quick submit, and hopefully that's good. Yeah, cool. I mean, and I was half confident, but you know, maybe I'd have a typo somewhere, but I'm too lazy to find it. But yeah, so what is the complexity of this, right? So basically, this is same as by first search, so it's going to be O of v times z. This entire algorithm is going. I mean, we said this in the beginning, but this is going to be O of v times z complexity. And why is this? Because each node on the graph will be processed by a queue at most once, right? Because we only put things in a queue if it is white, and if it's white, then you know it only can be white once because we change the color immediately, right? Except in this case, I guess for more consistency, I should move this here, but yeah. And for the yi, so that's the re part. The yi comes from the fact that for each node inside the graph, for each edge inside the edge list, we only do this if statement once, right? Like this only happens once for each edge, so it's going to be O of yi no matter what. So that's the complexity. In terms of space, we have O of v to store the colors, and that's pretty much it. So yeah, invite that here. I think that's all I have for this problem. Let me see if I have any more to say. I think this is it. Let me double check that I didn't block. Sometimes I block the screen and that's a little bit sad. But yeah, that's all I have for this problem. Let me know what you think. I will see you tomorrow. Happy President's Day, I guess. Valentine's Day, all those days. Take care of yourself, take care of others, to good mental health and to good regular health. And I will see you tomorrow. Bye bye.